Good afternoon, ladies and gentlemen, and welcome to the SAIEE Computing Chapter's webinar on quantum computing. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available under the Computing Chapter playlist on SAIEE TV. The link to register for it is in the chat box. It's free. I encourage you to do that. And a certificate of attendance will be issued a few weeks after this webinar once we've received the CPD validation from EXA. I'd like to introduce you now to our host tonight, Dr. Ndihuwa Mukondu. He's the Research Manager for Artificial Intelligence at IBM Research. He is, as I mentioned, the Research Manager at Artificial Intelligence and a sub-theme lead of learnable reasoning in the neurosymbolic AI research team at IBM Research. He is also a Senior Research Associate in Electrical and Electronic Engineering Department at the University of Johannesburg, South Africa. He received a PhD in Robotics and Machine Learning from the Tokyo Institute of Technology in Japan, and his BSc and MSc in Electrical Engineering from the University of Cape Town. Previously, he was a robotics researcher and team lead at the Mobile Intelligence and Autonomous System Lab at the Council for Scientific and Industrial Research. He also served as visiting lecturer at the School of Computer Science and Applied Mathematics at Wits University. Over to you, Dr. Mukondu.
Good. Thanks for the introduction, Mix. So I would like to welcome everyone to the first webinar of the Computing Chapter, which is a new chapter, of the Electronics and Software section of the SAIE. So this chapter covers different areas of computing, ranging from classical computing and all capabilities built on top of this, which includes AI, cloud computing, cybersecurity, all the way to the future of computing, which includes quantum computing, which is the topic of the day, and the translation of some of the capabilities built on top of classical computing to quantum computing, such as quantum machine learning, and so on and so forth. I am the deputy chair of this chapter, and I work closely with the chair, Dr. Joshua Maumera, who is in the audience with us. Together, we hope to consistently expose you to different areas of computing, and we'll be organizing many more similar webinars going forward, so stay tuned. Today, I'm happy to welcome two of my colleagues at IBM Research based in Braamfontein. They are working on various aspects of quantum computing. These are Gemma Dawson and Unathi Skosana. Gemma is a quantum community advocate at IBM. She has degrees in statistics and operations research. She was previously Vice President in 2019 and President in 2020 for the Operations Society of South Africa, among other volunteering work. She is passionate about community building and knowledge sharing, and she's skilled in explaining complicated topics. We also have Unathi, who is a research scientist intern in quantum computing at IBM Research. He's also a PhD student in physics at Stellenbosch University. He completed his master's degree in 2021 from the same institution. His research interests span quantum optics and quantum information science. So without further ado, I'd like to hand over to our speakers. Thank you. I hope you enjoy the talk.
Thank you, Ndivo, for the lovely introduction. Share my screen. I guess I can get started. Yeah, so my name is Unathi, as Nivor has introduced, and I have with me Gemma Dawson. And today our agenda will be quantum computing, and I will be the first speaker.
Sorry, Unathi, we're not seeing your screen. We're waiting to view your screen.
Oops, sorry. It seems like I will get kicked out of the meeting.
Sorry, ladies and gentlemen, we had a gremlin in the works, so therefore last minute Unathi is presenting instead of Ms. Dawson. So please bear with us while we sort this out.
This is completely my fault, and I apologize to everyone. So while Unathi is busy with that, I will, from memory, hopefully be able to give you a rundown of what we're going to run through this evening. So Unathi is going to go through the first half of the presentation. He will be looking at the information age and the origins of quantum computing, and where this whole idea has come from. He will then progress onto some of the more mathematical and phenomena that is quantum and explain that to us. You don't need to be worried if you are concerned about that. I know not everyone is super eager about the mathematical details, as some of us are. So he will, after that, we will have a break for a Q&A session. And then at that stage, Unathi will hand over to me. I will discuss quantum advantage, what that is, what it means, what problems quantum computers, what problems we expect quantum computers to be able to tackle, what problems we do not expect to be able to solve using quantum computers. And then in addition to that, I'll be moving on to the IBM quantum offering, what it is we have available right now, and what we are hoping to be able to offer in the future. I'll also be discussing IBM Quantum Experience and Qiskit. And then again, we will pause again for Q&A.
Unathi, can I make you presenter?
Yes.
Thanks. Okay, let's go. Let's try again.
There we go. There we go.
Perfect. Please proceed.
Awesome. So yeah, thank you. So I would like to begin. My bit of the talk will be sort of a high-level overview of our subject matter, and my goal is that the unacquainted leave with at least a rough idea of our subject matter, and that this will provide a germ for further inquiry and exploration on their part. So I would like to begin my talk by looking back into the past. Often historians associate the origin points of the information age to developments that took place in the 1940s. And they go on that there is a development of utmost significance, so much so that our modern age would almost be impossible to conceive without it. What I am alluding to, of course, are the mathematical inventions of the inimitable mathematician / electrical engineer Claude Shannon. Now, Shannon's inventions were the high point of an inquiry into a practical problem, namely finding ways of efficiently transmitting signals over a telecommunications channel. All right? And during this time period, telecommunications consisted of radios, telegraphs, and telephones. And vendors that made use of such technology were interested in these kinds of questions. All right? And Shannon's beautiful yet simple idea was that you could do away with the abstraction, or you could do away with the concrete and physical signal rather, and abstracted into mathematical symbols, of which he called bits, discrete values of zeros and ones. And with this, it allowed Shannon to define and quantify information in a manner that was independent of its physical implementation. And with this, he founded a new field of study we today called classical information theory. Now, you would have noticed that I used the demarcation classical information theory here. And this demarcation is quite necessary, as a few decades later, we would see information science branch off into somewhat two distinct threads. The later thread is on the back of a development that was almost antithesis to the former. In as far as Shannon had shown that information can be decoupled from its physical implementation, physics, of course, still has a say in all of this. In particular, Landau, an IBM fellow, definitively showed that physics places a theoretical lower limit on how efficient a computation can be. The so-called Landau limit, we see that it relates information, a somewhat abstract concept thus far, to physical quantities such as temperature and energy. Now, this mode of inquiry into the relationship between physics and information was further explored by a band of thinkers that included none other than the brilliant physicist Richard Feynman, who conceived and argued for the necessity of building a new kind of computer, a quantum computer, in tackling problems that were of interest to physicists at the time, such as, for instance, simulating quantum mechanical systems. Now, as you may be aware, physicists can have quite peculiar curiosities, and this one is not an exception at all. And one of the first questions you may ask yourself is, well, what need is there for simulating physics with this new kind of computer? Aren't conventional computers, such as the large HPCs we have today, apt at such a task? And if they aren't large enough, can't we just simply build larger and larger ones to simply meet the demands? Well, I shall endeavor to partially argue against the latter point and argue that it is not so straightforward as it may initially seem. And I will leave the latter point for later in the talk. Now, George Moore made the following empirical observation, that the number of transistors on a given silicon chip doubles at about each and every year. And he predicted that this trend would carry on well off into the future. Today, transistors can be as small as, for instance, 14 nanometers, which is about 500 times the diameter of a red blood cell. Now, as you can imagine, as transistors shrink in size, the chip industry is presented with quite a sizable challenge that comes along with it, huge expenses and a lot of research effort in maintaining this trend as observed by Moore. Furthermore, as transistors get smaller and smaller, you can as well imagine that we will simply reach a physical limit where it is physically not possible to just simply build smaller and smaller transistors. And when we get to such a point, we would have reached a physical barrier to our technological progress. which would see a slowdown in improvements to classical computing resources, which only escalates the importance of integrating quantum computing with classical systems. Now, you may wonder again, well, what makes quantum computers different, and how, if at all, can they allow us to at least solve some classes of problems which conventional computers may find difficult to solve? And one of the key differences is in the physical makeup of the aforementioned computers. As you may know, the most basic processing unit in a conventional computer is the so-called transistor, which in a nutshell is essentially just an electrical switch that can either block or pass current through it. Now, these two states of the transistor are abstractly associated with one, that is the on state, and a zero, that is the off state. And hence, we can abstractly associate the state of a transistor as a bit, as Shannon had shown. And from here on out, I'll refer to it as such. Now, transistors can be combined with one another to make up logical gates, which perform basic Boolean operations, such as an AND gate, for instance, which outputs a 1 if both of its inputs are 1 and outputs a 0 otherwise. And next in the hierarchy, we can combine Boolean logic operators to perform simple operations such as adding two inputs together. And eventually, as we get to the tip of the hierarchy, we can perform, complex operations such as streaming audio and video, as we are doing now. Where else the quantum computers that at least IBM built, they are housed in a structure that looks something like the schematic that I've shown here, which includes various parts which serve various functions. Now, at the bottom of this structure, there lies a processor chip, which has on it processing units analogous to transistors in a conventional computer. The processing units in a quantum computer are superconducting electronic circuits called transmon. And from a bird's eye view, they look something like this. The features you can see from here are made up of niobium, which is on top of silicon. And this is because at low enough temperature, niobium can allow electrical current to flow through it without any electrical resistance, making it a superconductor. And one of the features you see in one of the boxes is actually a parallel plate capacitor, which is also made up of niobium. And if you further zoom in, you will see that in between these parallel plate capacitors, there are tinier aluminum features. And these aluminum features are called Josephson junctions. And essentially, a Josephson junction is an insulating material sandwiched between two superconducting material. And what is important for our purposes here is that the Josephson junction actually electrically behaves like an inductor. All right. Hence, as a whole, the transmon device with an inductor and a capacitor electrically behaves like an LC circuit. The crucial difference is that the LC circuit has a nonlinear inductance due to the Josephson junction. And this is because, or the nonlinearity of the Josephson junction allows us to experimentally isolate the two lowest lying energy states of the transmon by giving them a unique energy gap, which would not be the case without the Josephson junction. And just like in the case of the transistor, we associate these two lowest lying states of the transmon with a 0 and a 1 state respectively. However, unlike the transistor, the transmon is a two-level quantum mechanical system, and we are now in the domain of quantum mechanics, which can be quite unintuitive. And yeah, so the transmon device is a two-level quantum mechanical system, which is often called a quantum bit, or I guess a qubit for brevity, and I will refer to it as such. Now, this new state of affairs is what bears the promise of quantum computers. And to aptly describe these, we need a new language altogether, and that is the language of linear algebra. Now, just like the transistor, or states of the transistor, the two lowest lying states of the transmon are associated with a 0 and a 1. And these, in this new language, they're mathematically described by unit vectors that live in a complex inner product space, as indicated on the slide there. And in such a space, we know that a general vector can be written as a combination or a linear combination of these two states. And these two states, the 0 and 1, with the symbols that look like a dash and a arrow, they are called computational basis states, right? So to rephrase this, you can say that a general vector in such a space can be written as a linear combination of these two computational basis states, where we further impose the condition that the square modulus of each of the coefficients should add up to 1. And now these coefficients are called probability amplitudes, each associated with each computational basis state. And they are simply just complex numbers over the complex field. Now, something peculiar happens when both alpha and beta are non-zero. That is, when the state psi, or the state psi corresponds to a quantum state with alpha and beta being non-zero, this is typically said to be in the superposition state psi. What this means physically is that whenever you measure what the state of the qubit is, which is the psi in this case, is that with a certain probability, you will find that you get the 0 state, and with another probability, you will find that you get the 1 state. And the probabilities in question are given by the square moduli of the respective coefficients. And until you actually measure what the state is, there is no way for you to tell which of these measurement outcomes will arise. The popular and somewhat misleading phrase is that the state of the transmon or qubit is both of these states at the same time. Now, to further contrast the differences between quantum and classical, let's consider an example. Now, consider a classical computation, say over a set of 4 bits, Now, throughout the computation, whatever the computation may be, is that the state of the 4 bits will be only one of these 16 possible states, right? Whereas, for instance, a quantum computation over a set of 4 qubits, we know that at some point in the computation, the state of the 4 qubits can be in a superposition state of all 16 possible elements, right, with various probability amplitudes. And this number grows quite quickly, and it does so exponentially. For instance, when you have a more even modest computation of, say, over 20 qubits, you already can prepare a state that can be in a superposition of over 1 million computational basis states. And by the point that this number reaches, say, something like 275, you already have more computational basis states than there are atoms in the observable universe. Now, one of the other phenomenon that qubits exhibit is known as entanglement. And this phenomenon occurs when 2 or more qubits in superposition are in close proximity to one another. And when this occurs, when 2 or more qubits are entangled, their measurement outcomes become mathematically correlated. And these correlations are quite different from the ones we see in ordinary life. For instance, if you influence an entangled qubit, say by way of measuring it, you actually also influence the other qubits that are entangled with it instantaneously across space and time, regardless of the separation between them. Another way to convey the same thought is to say that the state of entangled qubits cannot be described by independently referring to each of the qubit states. You can only describe the state collectively. Yeah, this is what is meant by that the measurement outcomes of the qubits become mathematically correlated. Right? And hence, the differences between classical and quantum computation actually does not stop here. As we've seen, the most basic processing units in a quantum computer behave quite differently from their classical analogs. And by way of implication, this carries over to the manner in which qubits are controlled to perform, say, computation. So, analogous to Boolean logic gates, qubit may be controlled by quantum logic gates, which are essentially just reversible operations that change the quantum states of 1, 2, or more qubits, for example. And the crucial difference is that a quantum logic gate can take as input a quantum state that is in superposition and produce as output another quantum state that is in superposition with different probability amplitudes according to how the quantum logic gate is defined. So by way of implication, a quantum logic circuit over a set. So by way of implication, a quantum logic circuit is essentially a sequence of quantum logic gates that act over a set of qubits. And this may include putting them in superposition or entangling them together, and at the end of which the qubits are collectively measured, and you get one of the measurement outcomes with a certain probability. But hold on, with a certain probability, as you can imagine, for any deterministic computational problem, at the end of such a computational problem, we expect, for instance, to get an outcome that might be possibly be a solution to our problem, rather than just some random outcome that is sampled from probability distribution of all possible outcomes. And is it possible that this can be the case, for quantum computation as well, since we have seen that, quantum mechanics has some indeterminacy built into it. And indeed, this is the case, at least for certain quantum algorithms. And one of the ways we can ensure that this is the case, we can cleverly harness the phenomenon of superposition and entanglement by way of interference. What this means is that we can manipulate or control qubits with a deterministic sequence of quantum logic gates in such a manner that the probability amplitudes of possible solution outcomes, say corresponding to our computational problem, add up constructively, while possible non-solution outcomes add up destructively, such that at the end of the computation, when we collectively measured the qubits, we have, or we can guarantee that there's a high probability that we measure one of the possible solution outcomes. And with that, I would like to bring my bit of talk to a close and hand over to Gemma to tell you about quantum advantage and what kinds of problems quantum computers can solve, and also let you in on some of IBM's offerings. But maybe before I do that, I can open up the floor for just a quick Q&A in case anyone might have any questions.
Thank you, Unathi, for such a great overview to quantum computing. Yeah, I think it takes quite a skill to present such a conceptual overview of a complicated field as is quantum computing. Do we have any questions from the audience? You can use the question tab to ask questions. I am not seeing any questions so far.
A few moments. All right, if there aren't any questions, then I would like to hand it over to Gemma.
Yes, I think let's move on. Please keep thinking about questions that you would like to ask. Okay, there's one question. William Stuck is asking if you can show the last slide.
This one.
Yeah, it's this one. So he's asking, what are H, X, and Z?
Maybe I can just go back one slide more. Yeah, so the H, X, and Z, they are actually operations or quantum logic gates that actually have classical analogs. For instance, the X gate is actually, or corresponds actually to the classical NOT gate in classical Boolean logic. But yeah, essentially the boxes containing one-letter alphabets in them, they're essentially just quantum logic gates, and they are defined as I have shown there on the right. Some of them, yeah, they do not have any classical analogs, but at least the X gate is one of the gates that has a classical analog in that it performs the NOT operation. So for instance, if your qubit is in the 0 state, what the X gate will do is when you apply it to your qubit, it will actually change it to the 1 state. And since these gates on that slide, I mentioned that they're reversible, when you apply it again to a 1 state, it will essentially just transform the 1 state to a 0 state. So classically, you can think of it as just applying the NOT operation. Yeah, some of the gates are quite difficult to describe in that manner. But maybe when we have time at the end, we can get back to this slide.
Okay, all right. Thank you. So yeah, I think we'll move on to the next session. Please keep asking your questions using the questions tab, and we'll have some time at the end. Okay, thank you. Go ahead, Gemma.
Thank you so much. Right, so quantum advantage. Unathi, if you move across. Now, quantum advantage is something that is under debate by the community. Every organization seems to have their own definition of it, but basically it's along the lines of when we reach a point where we're able to solve problems faster on a quantum computer than we are on a classical computer. John Preskill used this definition to define quantum supremacy, which is actually not a term that IBM prefers. Obviously, supremacy has very negative connotations, so we only use quantum advantage. So again, that comes into every organization, every person in the field seems to have a slightly different definition of what quantum advantage is. Now, we also have heard many times organizations announcing that they have reached quantum advantage on a particular problem instance, and then that results in a very fierce debate amongst the community as to whether that's true, whether it can be solved on a classical computer faster than they claim it can be. It is a very exciting and interesting time. But once we do reach that quantum advantage, where I think most of us would agree, is we would have reached the quantum age. We're now at a point where quantum technologies are a part of our everyday life and decision making. If you go to the next animation. So IBM is very much of the opinion that this is possible in the next few years. And this is not going to be everything all at once. It will hit different industries and different problem types in different timelines. So if we go across, what are those problem types that we're looking at? What can quantum solve? Well, right in the middle, if we go to the next slide, we've got problems that we can address and solve classically today. That's multiplying bit integers, that's reading emails, that's streaming videos like we're doing right now. Where are we sitting with quantum? Why have quantum if we can solve these problems? Well, you know, we look at problems, if we go to the next slide, we look at problems that are in many instances just too large to solve classically. It requires too much data, or it requires too much time, or very likely a combination of the two. So factorization of large numbers. We've got simulating complex molecules and optimization problems, which me as an operations researcher, that's really where I enjoy playing around, and I'm very excited about this. So they're not easy to solve classically, and we are hoping that at least for the majority of these problem instances, we'll be able to solve them with a quantum computer. If you go across to the next slide. So yes, so we're very excited about this. Next slide. So what is not possible? Well, there's a group of problems called undecidable problems. This is one that should give a yes or a no answer. Sometimes when you lay out the problem itself in a simple word problem, it seems very simple. But the reality is some of these problems we'll never be able to solve classically, and we'll never be able to solve them on a quantum computer either. Quantum is not a magic wand that comes in and solves every single problem we've ever come across. A few of these undecidable problems is the halting problem, Conway's Game of Life, and Magic the Gathering. And in terms of Magic the Gathering, we're looking at whether a player has a winning strategy. That is something we simply cannot determine with an algorithm, whether we're using a classical quantum computer. To the next slide, please. Now, if you are interested in the P-space, NP hard, NP complete, P problems, that whole fun mathematical explanation, there is a fantastic blog post that explains all of those concepts, and it explains what a quantum computer can actually do within these problem spaces. So please use that link. Go ahead, read that blog post. It was written by Bryce Fuller and Ryan Mendelbaum. Next slide, please. Now, we've talked about problems generally. What are these applications of quantum computing? So if we go ahead, click the next slide, we're looking at improved nitrogen fixation process for creating ammonia-based fertilizer. Now, it is estimated that about 1 to 2% of the world's energy consumption actually goes to producing fertilizer. Now, if we can reduce that significantly by using quantum computers to find better processes, then we are making an impact on our global footprint. To the next slide. New catalysts to make CO2 conversion into hydrocarbons more effective and selective. Next. Better financial models to improve stability, predictability, and the growth of world economies. And of course, next, having a look at new classes of antibiotics to counter the emergence of multi-drug resistant bacterial strains. Next slide, please. Now, what is IBM's offering? Well, one of my favorite places to play is the IBM Quantum Experience. Now, this has been around since May 2016, when IBM offered it up free to the public, where people could log on, create an account just as you can do today, and immediately have access to, at the time, 5-bit real quantum computers, as well as quantum simulators. Now, initially, you were only able to play with quantum circuits and using a GUI, kind of, you'll see in an image just now, drag and drop and create a quantum circuit. But nowadays, we then introduced in March 2017, Qiskit, which I will touch on again later, and you're now able to write code and interact with quantum computers. So what else is on offer? What is available right now? We have the ability to learn quantum computing in the quantum experience. So you're able to access the docs, as you can see in this image here, but more than that, you're able to access tutorials, you're able to access a textbook, all of that right there, super, super close and handy. Next, please. In addition to that, you're able to view the quantum systems. So what quantum systems does IBM have on offer? What do you have access to? So nowadays on the public access offering, the free offering, you are able to access both 5-qubit and 7-qubit quantum computers. And if you upgrade to the pay-as-you-go, you're able to access 27-qubit computers. If you are part of the premium offering, or you're an IBM partner, then you can access all the way up to the most recent 127-qubit computer. Next, please. In addition to that, you can access the Jupyter Lab notebook within the IBM Quantum Experience and immediately start coding with Python and with Qiskit. Now, this is what I really am excited about, because it doesn't require you to have the correct version of Python installed on your machine. It doesn't require you to have all the packages downloaded and the version control and all the drama that can sometimes go into these things. You just log on to the IBM Quantum Experience. You're connected immediately to quantum computers. You can go import from Qiskit, import star, and you can immediately send a job off to a quantum computer within moments of creating an account. And then, like I said, you know, our initial offering was the graphically built quantum circuits using GUI. That is still available. It's being improved upon and being used in research and development. Right, so in the next slide, we'll see Qiskit and we'll learn a little bit more about that. So what is Qiskit? So if you just go ahead a few slides so we get the full SDK architecture, please, Unathi. Qiskit, as said here, is a software development toolkit. It is built in Python. So if you know Python or you're learning Python, this is not a completely new language to be learning. As long as you've got your Python skills, some mediocre Python skills, in fact, you can start interacting and coding, which is very, very exciting. Next slide. Now, to me, Qiskit is more than just some lines of code. Qiskit is definitely a community. Now, Qiskit is open source, so it is not just IBM determining the future of this product. It is not IBM creating all of the code, maintaining it, though we do play a very, very active role in that, and this is truly is one of our babies. It is open source, so there is a wider community of developers and researchers and academics and hobbyists and beginners who are actively involved. The Qiskit ecosystem is more than lines of code. It's projects, tools, utilities, libraries, and tutorials. If we go next. Now, what can we do with Qiskit? Research, development, and learning. These are all the exciting things. So go ahead, let's have a look at research. Now, the exciting thing about research, if we go next, is based on the usage of our IBM systems, Qiskit has been involved in more than 1,400 research papers, which is phenomenal. And we do regularly look at the stats and what's going on with that. And every time we pull up graphs of Qiskit and IBM systems, we're always completely amazed and overwhelmed. So that's Qiskit. Now, what is very, very important to understand is that Qiskit, yes, you know, we've built it to work with IBM quantum systems, but we are not exclusive to IBM. Just as I said, this is community run. So if you are interested in working in Honeywell or Getty or Amazon Bracket, you can switch out the IBM quantum system and swap that in, or work with all of them and do comparison studies. So if you go ahead, please. In development, we've got Qiskit Runtime, which is a relatively new offering. It did come out last year. This allows us to optimize workloads, efficiently execute at scale, because as soon as you are paying for quantum systems, you want to get you want to reduce the runtime. So Qiskit helps us to do that efficiently. It helps us to optimize that. If we go ahead to the next line. We also have the Qiskit application models. We would have seen this earlier. You can see here finance, nature, optimization, machine learning. And the focus of this, the goal of this is really to create an underlying technology that is no longer a concern to users. So basically, when I sit down as a data scientist, I am really not concerned. I don't need to be too worried about what is happening between my keyboard and my desk. I don't need to be able to build that. And that's exactly what we want to give you with quantum computers as well. You don't need to have a PhD in physics, though if you want to get that, you go ahead and do it. You don't need that. You can start coding, and with a few simple extra setup steps, interact with a classical computer, interact with a quantum computer, and it feels pretty much the same thing. Next, please. Now, I was a teacher for 10 years, so for me, learning is something I will never be able to let go of. One of the most exciting things I've watched over the past year at IBM is the development of the new version of the textbook. So Qiskit textbook, it is open source, and it holds university level courses around quantum algorithms and computations. We've got inline, built within the textbook, Qiskit code cells, so you can interact, you can immediately implement what you're loading in the paragraph above and see what happens. You can start then playing with that code, changing a parameter, see how the results change, which is very, very exciting. This is truly the top source of quantum computing knowledge on the web, and is really only second to Wikipedia, which is just, to me, a mind-blowing thing. If you go across to the next slide, now we've got more than just the textbook, but you can easily access from the textbook, you can access it from the IBM Quantum Experience, tutorials, you can access the resources, the materials from the 2-week-long global summer schools that happen once a year, the 2022 summer school, which was focused on quantum simulations. Those materials and videos will be up in the next few months. We've got additional resources, obviously Qiskit YouTube, which I've directed to you to, the Qiskit Medium blogs, and then of course we've got IBM Quantum Challenges, which happen quite frequently and are just fun ways for people to learn, to get involved, to challenge themselves, to work as teams. We've had over 1,000 participants in our challenges over the last few years, and always exciting time when we've got a new challenge coming up. Next slide, please. Next. Sorry, we're going to skip over that. Now, the road development, next steps, what are IBM's next steps? In November of last year, Jake and Beta announced the Eagle, which is 127 qubits, and hopefully we're on track to announce an even bigger machine at the end of this year, fingers crossed. So we're looking at 433 qubits, and we're also hoping to have dynamic circuits start to play a big role in our developers' lives. Next, please. What about your next steps? So personal development. I have mentioned the YouTube channel, I mentioned the textbook, I mentioned the challenges, the summer schools. What I haven't mentioned yet is the Qiskit developer certification. So once you've moved across, you've learned a couple things, you now want to be certified, you want to have a badge on your LinkedIn, you want to be able to add that to your CV or your resume and say that you are truly a quantum developer. You can take our Qiskit developer certification. We regularly do hand out vouchers for that, and a world recognized qualification, and very, very exciting to get that. If you are interested in taking this exam, please do reach out to me. Now, if you are involved in formal research or you are interested in partaking in some formal research, what is important to know is that Wits University is an IBM Quantum partner. They are the only one on the African continent, though they do offer a bit of a hub experience in that if you're a part of Stellenbosch, KwaZulu-Natal, universities that are in the Aurora network, you are able to access the premium IBM Quantum devices through Wits University, which is a very unique partnership and a very exciting partnership for the continent. If you are interested, please do reach out to us. We are often looking for academic partners, research collaborations. We're able to connect people, whether you're a non-quantum expert that wants to be involved, or whether you're a quantum expert that does want to be involved, please reach out. We can make those connections. And then accessing those big machines, the 127, and maybe at the end of the year, the 433 qubit machine. We do have the IBM Quantum Researchers Program and Access Awards. So we do recognize that it's not just IBM's work that is going to push this field, and we do try and reach out and help researchers access these big machines so that we can all as a community work together. Next slide, please. And then I am an IBM Quantum community advocate. So to me, the community is just absolutely amazing. I've mentioned before the Medium blog, the Twitter account is very active, making sure to share. We do have a public Qiskit Slack workspace, so you can easily Google that, find that, reach out to me if you're needing some help. We have LinkedIn groups that are very active, so you can keep on top of the most recent news. And my new passion project, the Qiskit Advocate Program, because as of Thursday, I will become the program manager for this. Qiskit Advocates are an amazing group of people who have shown that they are contributing to the community via open source, so whether it's code, whether it's organizing events and hackathons, there are many different ways to contribute. And they get many fantastic perks because of this. So if you're curious, do a Google search, please reach out to me. And again, if you get accepted, it does come with a badge that you can show off on LinkedIn. And if we move to the next slide, I think we are almost done. That is it. Right, any questions? I think I did see something pop up while I was talking.
Yeah, we've got a couple of questions. I don't know if we'll be able to answer all of them. We have 5 minutes left.
You can try.
Okay, well, I guess I'll start with one that just popped up. How much usage has quantum computing had in the field of AI to date? From Jimmy Kosa.
Sorry, could you repeat that?
How much usage has quantum computing had in the field of AI to date?
The field of AI.
Yes.
Okay, so I mean, we've seen there are a lot of research papers, there are a lot of exciting things that are happening. There are also a lot of open questions. So like I've said, we haven't kind of reached that quantum advantage where we are 100% it's happening, we know it's happening. In terms of AI, that's not really my expertise so much. I know one of my ex-colleagues, Amiri, she's been doing the most phenomenal work in machine learning and has published many different papers on that. For me, that is the best answer I can give at this time. I don't know if Unathi has anything you would like to add to that.
Yeah, same here. Also, machine learning, I guess, is my domain expertise. Maybe I'll just not attempt to answer the question.
Okay. There was also a question relating to the first session, which is in terms of the hardware, how are these circuits implemented? I mean, that's for Unathi.
That's a very good question. So typically, Transmol, the quantum logical operators that actually implemented through microwave pulses. Like, depending on how you shape the various microwave pulses, you implement various or different gates. For example, one of the gates I've seen on one of the slides that I showed you, control NOT gate, which has a classical flow of holding or applying a NOT gate whenever a certain bit is one state. So the analog of that quantum mechanically is implemented through a process called cross resonance. But yeah, essentially the quantum logic circuits or quantum logic gates in the quantum logic circuits, they are implemented by way of microwave pulses that are channeled into the processing chip. Hope that answers the question.
Yeah, thank you. I mean, Gemma, I remember we had one of the quantum computers, IBM quantum computers here at the lab in Braamfontein. Where is it based? Is there any chance of getting it back?
We've actually had some recent discussions about that. Yeah, so we were very lucky in 2019. We had the IBM Think event, and that's where we actually have announced the Wits University partnership, which was the first on the African continent, which is very, very exciting. And in addition to that, we had IBM offered a quantum summer school, because it was December here, for students all across Africa. And from those 2 weeks, we went into Camp Africa, which I was very lucky to attend. I wasn't an IBM employee yet, but I was able to attend, and we had a hackathon out in the Pilanesberg, if I remember correctly, which was my first proper experience hands-on interacting with a quantum computer. And all during that time, we had the most beautiful quantum chandelier. I think we've missed a bit of an opportunity to get the golden picture up here on our slide deck. And it lights up, and it's just absolutely magical. Yeah, so hopefully we'll be able to get it out here again. The chandelier obviously sits within the actual quantum IBM Quantum System 1, and hopefully, not too distant future, we'll be transitioning into the Quantum System 2. And it sits at the sub-zero temperature. It's mind-blowing how cold it needs to be in order to run. So what we see as the chandelier is lights up and flashes around and might be representing real jobs that are being sent to quantum computers, but it itself is not running those jobs itself. But yeah, hopefully one day soon we'll be able to get it back in South Africa. It is quite a big, delicate operation. So of course that comes with a very big price tag. So we need to have an event worthy of bringing it in.
Okay, but do people have like access to, programming a quantum computer, like through the
100%, yeah. So we've got all the access. Like I said earlier, if you sign up, create an account on the IBM Quantum Experience, you can either start working immediately in those Jupyter notebooks and send jobs off to real quantum computers. Those quantum computers are based, unfortunately, everything's sitting in the Northern Hemisphere. We've got sitting in the US, obviously, our research headquarters are there. We've recently set up some machines in Korea and Japan, and I think we're working on a second machine in Germany. But yeah, you've got access to those machines immediately. If you are wanting to work on your local machine, IBM Quantum Experience, you get your OPI token, and you can start interacting from there as soon as you've downloaded the right packages and got set up.
Okay, thank you. We are at the top of the hour. So with that, I'd like to thank our speakers for their efforts in making the time. Also, thank you to the attendees. I hope you'll be joining us in this computing journey going forward, and we'll be bringing you more talks of this nature going forward. So stay tuned. Thank you.